TensorFlow run as a LSTM for text. What is LSTM? Anybody knows? So that seems like translation, predicting the next word, takes into account a lot of the word context, dependencies, and order, right? Yes.
Do we use LSTM for classification or predicting?
You can set it up in various ways. The ones that I'm most familiar with is predicting some sort of event, predicting the next word when you start typing, and machine translation. So it's not exactly supervised learning in a standard sense, but you have to feed in, if you do translation, right, from say English to Spanish, you have to feed some training set that this sentence has been translated into that before. How it's going to learn the pattern if you don't feed anything.
There's no more like what are we using?
For those things, I don't have a clear specification yet. So I can imagine a translation task, for example, or a predictive task, for example, for the next word. I think we can find plenty of examples. I don't have a data set, but we can find an example of English to Spanish. I think English to Spanish should be a lot easier than say English to Chinese, but I'm not an expert at that kind of task. I don't know. My intuition tells me that English to Spanish is an easier translation. Or we can find this predictive, once you start typing, predict what the next word is. In CNN, you should know that a lot of the usage of these, CNN is a complete pipeline that does classification, but a lot of usages are just to extract the image features. We talked about this before. A lot of the big data companies they do images like Facebook, they would run such networks to extract featured images. That's our plan, and Yu is going to come today at the end of the lecture to talk about this, word vectors. Okay? Like before, you're going to run a package. You don't implement yourself. You have to set up TensorFlow, but those scripts are already on the internet, not too hard to find. You're going to have to show us how your word vectors work. So the purpose of this is to map a word into a set of an array of, say, embedding in 300 dimensionality, right? So every word becomes, this is an array in real numbers 300. Every word becomes a vector of 300 real values. Right? That's the purpose. Embedding generally refers in data science as taking some object, in this case a word, some other cases a document, an image, a paragraph, whatever, and put it in a dimensional, Euclidean dimensional space as a vector of real numbers. So when you hear the word embedding of images, embedding of patients, embedding of emails, it means typically create a Euclidean space of roughly 300 to 500 to 800 dimensions, in which all these objects have coordinates. Right? So in that sense, you can think of this as those are features for words, if you like, right? Like before we had features for documents or for images, now we have features for words. So there's a lot of downstream tasks that are applicable here. We won't get too much into those. So the purpose of the homework is to study the embedding of words alone. There's a very legitimate question, why would I need embedding for words? What do I do with them, even if they are very good? What can I do with such embeddings? Because you really want embeddings for documents, or for sentences, or for tweets, or for emails, or for patient records, right? Our objects so far were never the words. Whenever we cluster or classify, the objects were documents. So there is a question that we're not going to address in this class, unless you want to do some sort of project. Once I have embedding for words, how do I use them? For this homework, in this particular problem 4, we're going to worry about how did the embedding of words are meaningful. So you're asked to do two things. One, to compute some similarity based of your embedding. Like you take two words, Based on this, you can compute a similarity or a distance, and you say, okay, for this word, I have these other words that are similar to it in my embedding space. And another thing that you can do is to project this space in 2 or 3 dimensions like I showed you last time and plot those words to see all of them. And the magic of this procedure that's done through, it can be done two many ways. You guys are going to do it to TensorFlow. Is that the embedding depends on the data you have. You should notice that if you run the procedure on a text that say Wikipedia, you get a certain embedding. You get, now you stop, you get tomorrow you do an embedding on a different piece of text like 20 news groups. I mean all the documents from 20 news groups, you get a different embedding. And then Google has some general embedding that they've done over a lot of documents from the web. Literally, they have 1.4 million words, because if you look at all the web, you see almost all the words. In practice, in English, there's only about 100,000 or 150,000 common words, but if you look at all the web, you see a lot of them. So it's not easy to tell from the embedding alone whether two things are the same or not. Even though the embedding obtained on 20 news groups is not the same as the embedding obtained on Wikipedia, say, it might be that just the rotation or translation of these vectors corresponds. It's perfectly analogous. So what we need to do when we have two embeddings to compare them, we need to measure the relative distances between things. That should be clear from the homework 1, that when we represent stuff in multidimensional real vectors, we can't immediately tell if this representation is the same or not as this other representation. Because even though they don't have the same values, they might be a rotation translation of those that will give me the same more or less thing. But if I start measuring distances between objects per ij, and I measure the distance of the same objects here, if I see very different distances, that means it's a different embedding. So that's the purpose of this problem. We're gonna move on right now. I'm done with TensorFlow, but you guys are just starting. So Yu's gonna come talk about this, and we might have more demos next week if necessary. Okay, so we need to move on with the lecture. So now what we're gonna do is to study something that's called topic modeling. It's particularly applicable for text. Although the techniques in here could be applied to other data points if we want, but we won't get into that. So let's see. Conceptually, we have a lot of text, say 20 newsgroups. Let's ignore for the moment the labels. Labels are usually a bonus on data, and usually an expensive bonus. It's usually hard to get labeled data. If you think about how many images are labeled, or how many documents are labeled, versus how many documents are not labeled, it's roughly 100-to-1 ratio. It's a lot more data that's unlabeled than the one that's labeled. And good labels are very expensive. The more noise-free you want to label things, the more you have to hire experts, and a lot of them. This is a well-known user studies done over the last 15 years that Microsoft and Google and so many other companies, hospitals too, they hire professional people to label their data to make sure they get noise-free training sets, for example. But there's a lot of less quality labeling, for which we can get random people to label things. If you heard of Mechanical Turks, for example, or Crowdflower, those crowd systems, right? You can get cheap labor there. You can get people to do the job for you, but their reliability is very low, right? You can count too much on those. So you have to hire many of those to get a reliable outcome. So let's ignore the labels for the moment and say we have those 20 newsgroups articles. So how these articles look like? So 20 newsgroups as an example, or we can take Wikipedia articles. those are essentially a bunch of docs. Doc 1, doc 2, doc, say n, represented as words. Right? So this is word 1, word 2, word, I don't know, D, if we have D dimensions. That's a standard matrix that we've been looking at forever, right? That's the raw matrix. Now, you could say, okay, if this is a count here, right, we call it TF, right, the term frequency of that document, that word, how many times the word appears in that document. You could say that that's not really representing the raw data because the text is not just the counts. There's order, there's semantic meaning, there's expression, there's bigrams, right, so on and so forth. So you can complicate the thing to say add positioning or ordering. As a form of raw data, I don't want to think for right now of it as a matrix. I want to think of those as raw data. And if you don't like this, you can create a nice information retrieval indexing platform to get the better form of the raw data. So what do we want with this? It turns out that most text, which is not a collection or large collection of documents, say the web is too big for this, right? The web contains everything. But 20 news groups is not everything. It's a bunch of articles written or collected for a bunch of purposes, like those 20 classes, or collected from a certain part of the world. I don't know, from UK, for example, if I read UK news. Most documents, when you look at them, they are specific to something. They are patient records, they are emails, they're bank fraud, there's something with to do this. It's not just a general random collection of text. So the question is, can we somehow find, similar to k-means if you want, some sort of clustering? We want to move this into, we want to introduce this middle layer here that we're going to call topics or clusters, such that, let's say we have a bunch of them. We have k, like in k-means, we had k clusters, such that if we look at the documents, doc 1, doc 2, doc n, and if I look at the words, word 1, word 2, word D, there is a nice interpretation of each one of these. Each document has some interpretation, some representation into the topics. So what we want here is to say a document is a representation into topics. So some form of, is that topic or that topic with some probability or some confidence, right? In other words, we want to say this document is about business and politics and economics. My topics could be those three: business, politics, and economics, right? So those topics have to make, they have semantic sense. That's a major difference to k-means. In k-means, when we do clustering, we group those things. We hope that those clusters mean something, but they sometimes don't mean anything. In topic modeling, usually, if not always, we want those topics to mean something, to make some sense. So the topic you can imagine being as a whole sort of hidden layer, but it's not like in neural network something that we don't understand. It's something that we explicitly want to put our hands on and understand what the topics are in my 20 newsgroups. And then we want the documents to be represented into those topics, but also the topics to be represented into the words. So documents in here are represented now into topics. And in here, what I'm saying, this part, is that we want topics to be a representation of words. So we want to introduce this middle layer somehow, that in a graphical model sense, kind of creates independence between the two. Now we don't have documents depending directly on words, which of course we had here. In raw form, documents were represented as word counts or positions or something. But we want to add this layer and say, once I add this layer, once I do my computation and I get those, I would like now to have every one of these, say a topic could be a complicated thing, like, I don't know, Catholic Church. Catholic Church, are we familiar with what it is, right? It's a topic that has to do with a lot of words. What might be some words related to Catholic Church? Huh? Jesus Christ, that's a big one. What else? Pope. Popes. We all know what the popes are. I know most of you are not Catholics, but you heard of the Pope, right? He lives in Vatican, right? Big guy. Okay, what else could be related to the topics Catholic Church? Demons, heaven, all of that. What else? God. Although God, as a noun, it's in many religions, right? I mean, it's certainly more related to Catholic Church than to say, I don't know, mathematics. But God as a noun, not the God, the Catholic God. God as a noun is in all religions. All religions have gods, right? A lot of the feudalism and all politics in feudalism was based on Catholic Church. Bishops, now they don't have as much power before, but before they were very important figures in people's lives, right? Now, church is just one of the social things that people do. Before, church was the absolute integral part of people's lives, including the government. All right? So, see, a topic like Catholic Church is not simply to say, okay, if I wouldn't have this, my only hope for Catholic Church, if I want to do some sort of matching or understanding, I don't know, maybe some of you took information retrieval, but even if you didn't, think about searches on Google, right? If I don't have this, what do I do if I'm Google and somebody types Catholic Church? Well, how do I produce documents? Search for Catholic and search for the word church, right? Keyword search, which is easy, right? Because I have the indexes, so I can immediately tell what documents contain the word Catholic, what documents contain the word church. That's a well-solved problem, right? But the problem is the Catholic Church is a very complex topic that a lot of documents that don't have specifically named the word Catholic and the name church might be very relevant to that, right? It's not the same as I'm typing an address. If I'm typing an address, right, like a navigational query, I'm literally looking for that place. That's it. Keyword search will work. Or if I'm typing, I don't know, some sort of movie and I want to get to the IMDb page of that movie, I can just search for the movie keywords, right? But for things like that, that's a very trivial example. The topic models are used for much more than that. It will be useful to have something like Catholic Church represented in terms of many, many words that could be related to this. And not just as a collection, maybe I need to have some weights. Catholic Church might be more related to that word than that word. I need to represent this somehow. So this side is a way to say, can you summarize the text for me into main chunks? Like, it's particular for every data set, like for 20 news groups, we should see certain topics, but for spam base or for other data sets, other text data sets, web pages or Wikipedia pages, we'll see a different topics. Once I have the topics, I want to represent my data being documents, not as the words. I want to represent them as, say, confidence or weights or probabilities over those topics. So you can think of this similarly how we thought in the previous module as a dimensionality reduction technique. right? Because words, D could be what? 100,000 easily, if not bigger. But the number of topics I'm going to get is not going to be 100,000, right? If I do 20 news groups and I'll say, give me the topics from this data, maybe there's 100 topics in there. I don't know. Maybe 100 is too small. Maybe some data sets will have 1,000 topics of interest. It's very specific to the data you have. Again, you have to, when you do this for real data, you have to pause yourself and think, as a human, not as a computer, I'm looking at these documents. What are the important aspects of this data? So I'm a bank and I study loans, right? And part of the application has to do with text, blah, 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 blah. There are, how many things a banker will look at when he sees these applications? They probably like 5, 6, 8 things first before they decide to move on or not. Whether you are employed, whether you have an education, what's your age, things like that, right? So even though, say, these applications or patient records, if you like, could contain a lot of words, a doctor or a banker will look at very few things to make a determination of what's going on. In that sense, we don't need that many topics, right? Because those topics should correspond naturally to what would a person look for in a document. There's a question?
Yeah. So essentially, you said that topic is something we decide, or does the algorithm come up with like set of topics?
We don't decide the topics, although that's a very nice follow-up. So there's research now into that. Suppose I already know 3 topics, because I'm a doctor and I already know what to look for. Can you find the other 7? So that's an interesting way to pose this problem. But the version we're going to do, we're not doctors, we don't know what's going on, and we just specify K, like in K means, and then we say we want 10 topics. The algorithm's supposed to give us 10 topics. Question?
Yeah, how do you decide how sparse the topics would be? So it can be, say, as basic as stemming robots and
Yes.
So,
So there's two decisions. There's design decisions, which basically comes down to K, right? But then there is algorithmic decisions, which is, okay, how do you do this? Because you could say, I could have done PCA, right? I mean, I think you guys tried this, right? PCA on 20 news groups, right? Didn't work so well, maybe. So if I do PCA, I get some sort of dimensionality reduction. Those features, I'm asking PCA for 20 features, for 100 features. Can I think of those features this way in PCA? So suppose I start with document versus words. I run PCA. Now the new dimensions, I get the representation of my data into the new dimensions via PCA. Do I get that?
Yeah.
I definitely do. How about between the PCA dimensions and the words, which were the original dimensions, right? Is there a relation there? What? Yes. Is there a relation? So we all know the PCA produces a new representation of the data, which is every single document or image, whatever I had, now is represented as a vector of the 20 things that I have. But is there a relationship between those new dimensions and the old dimensions? Can I say, look at this first dimension of PCA. That corresponds to what?
yeah, similar features.
There's some linear combination of the old dimensions that give, in fact, that matrix P in MATLAB.
Yeah.
What it does, it says, the reason we get PCA, the new representation X prime, X new. Remember it's P times X? Once we get that magic P eigenvectors times the eigenvalue square roots. The reason this happens is that these are the coefficients that allow this relation to happen. It says every new column is a linear combination of the old columns. So these are literally the coefficients that make the transformation from the old features to the new features. So in some sense, we already solved that problem, right? Didn't we? PCA will do this for us, right? But it didn't work so well for text, did it? So we're gonna try to do this in a better way for text than PCA. But as a basic notion, if somebody tells you this is what you want, can I run PCA? Technically, mathematically, sure. Because PCA will give me some representation of data into new features, and it will also give me new features versus old features. So it is an intermediary middle layer that's well defined mathematically, not necessarily very useful for text. So there's two main approaches for how to do this. One is, I've already talked so far about the design. What do we want to get out of it? And the only parameter we have so far is K, which is nice because we only have one K, like in K-means. We say how many topics we want. This K, it's almost invariably determined by humans with practice. People who know bankers look at 10 things, so they ask for 10 topics. People who know doctors look at 25 things in patient records, so they ask for 25 topics. That's what you guys gonna do. You're gonna try to plug in the K that makes more sense. But now algorithmically, how can we design this thing? We can say, I put these arrows here, or these lines, but we have to instantiate this into math now, right? What do they mean? Okay, so there's two versions for this, and we're gonna spend the next 2.5 weeks dealing with this stuff. One option, it's called latent yield threat allocation, or LDA. This is a probabilistic model. You can call it mixture. Mixture may sound familiar to the EM. Remember the EM homeworks where we're trying to determine a mixture between things? So one philosophy is to think about this as a mixture, to say, in here, we're going to think of a topic as a distribution over words, and a document as a distribution or mixture over topics. Now, so this version, it's gonna be heavy on probabilities. As in so heavy that we actually can't do it. We don't have enough mathematical support to do this. We need to learn a lot more mathematics. But it's useful for you to know, at least conceptually, what is this trying to do. Of course, there will be some sort of, okay, here's an equation. Let me try that. Don't get scared. I'm taking this from this particular tutorial. There's many ways. Every single paper has a different version of this. So okay, isn't that nice? So let's try to make some sense of what's going on here, right? Let's do the easy part first. Alpha and beta are parameters. Parameters, not just parameters, parameters of assumed distribution probabilities, shapes. See, what happens with probabilities or generative methods in general in data science, every time we have something like this, probabilities, the only way to solve it is to make some assumption about those density functions, like they're Gaussians, or they are exponentials, or Poisson, or Dirichlet, or something. We don't know how to solve mathematical problems with probabilities in general if we don't make very specific assumption about the densities. Just like happened with EM2, right? We said, let's assume they are Gaussians. And then what were my parameters if they are Gaussians? Before, what did we look for? When we tried to figure out that mixture in homework 2, right? We say they're Gaussians, that was an assumption. So if they're Gaussians, what would be my parameters? Sigma, variance, whatever Gaussian functions have. Now if there's gamma functions, there's alpha and beta, like in the beta distribution, I don't know. Every distribution has a bunch of parameters. So these parameters will only be there depending on the assumptions one makes. Exponential distribution, how many parameters it has? So there'll be a parameter. But if you make a complicated assumption, you're going to have a lot of parameters. Right? So that's always going to happen with probabilities models. Who is this WJ? It's easy. That's word, I think. Word J. I think. I think theta is also parameter. Sometimes theta is just alpha and beta. Usually we don't worry about those because they come out of estimations, very mathematical estimation steps. Word, this W is a word, right? Make sure I don't say bad things here. And who's ZK? Topic. So let's start reading this formula from kind of the right side. What's the intuition? What is the probability of a topic, right, times the probability of the words given that topic? So that sounds a little bit like what we wanted here, right? I think a probability of a word given a topic relates to what side of the things? This side, right? That has to do with how words, hard topics are defined in terms of words. You know, in probabilities, we can change the conditionals the way we want because we have the Bayes theorem. So it's either ZK given the word or word given ZK. Either way, we have something related to here, right? This is like a mixture, right? That does not depend on, it's like a prior, you know, in mixtures when we have that mixture coefficient, it's the mixture for that topic, right? And maybe that's why we have a sum here. Remember the sum that we have of the components for mixtures? And then things are more complicated. I think this is a likelihood function, must be. Likelihood means the probability that this document D that has those words can be represented like that over the topics. So remember, we want the topics to come out of this algorithm. We're not going to specify in advance what the topics are. But we would like to say that topics are a probability model over words. So when this whole procedure is done, we like to say topic 1 contains words, the following words with the following probabilities. And the documents are on these topics with the following properties. So now, we may want to make a product of this, I think. Let's leave it at that. This is a document. If I want to evaluate the likelihood over all my data set, just like in the likelihood regressions, I'm going to have to make a product over all documents likelihood. And then I have to optimize this function. Meaning, what do I have here? I have the number k of topics. I have the words. I know what words appear in what documents and how often. And I have to run some mathematical optimization procedure to obtain what? To obtain the parameters, right? The parameters that will give me the best likelihood or the minimum objective.
Do we use EM?
We can use EM, sure. So that's a good idea. EM as a solution for maximizing likelihood. That's definitely possible, but not very good. People have tried many things, and they got stuck with EM most of the time. But EM, because this is a mixture-based model, will have this. I don't have here a EM update, but I think in this other paper there's an EM formula that does the update. No, so everybody is doing something else. Something that we have not done at all, and I'm afraid it's, like I said, beyond what you have done. So I'm going to say here, how about Gibbs sampling? How many people have heard of Gibbs sampling? One. Okay, what is it?
No, I'm part of it. Yeah, most ones.
Yeah. So Gibbs sampling has to do with, it's very good for Bayesian type of problems like this. Gibbs sampling says if you have a distribution of many variables and you like to sample from that distribution, and there are a lot of dependencies, you don't want to do it independently. I'm telling you a very childish story right now, okay? I would like to turn the camera off so I'm not on record with it. So what Gibbs sample says, how about I sample in some order from this variable, because I have to start somewhere. And as I keep sampling, I account for the dependencies of the new things that I sample versus the old. So I pick this order, which could be good or bad, but I pick an order of the variables and I sample from these variables. A data point is a vector, right? So I sample it in order. But then as I move as I keep sampling, I'm keeping track of the conditional distribution. So I'm trying to match, given what I sample already, the conditionals. This is very applicable when I have a lot of conditional distributions that are easy to control, like in Bayesian formulations. In Bayesian formulation, there's a lot of conditionals that we evaluate explicitly. But the joint is a mess. So what people have proven that with these methods like Gibbs sampling is not the only one. Once you do the sample, even though in the beginning the samples are not very representative for the distribution you have, you can start computing marginals and expectation values so you can evaluate what you want to optimize for. In most problems, this is a immediate replacement for EM or the other way, but it's not clear where you want to use EM or there's a fancier method than EM. It's called variational inference based on the same ideas. Versus when do I want to use sampling? Sampling maybe sounds more familiar if I call it a Monte Carlo method. Right, so it's one of those. So what we're gonna do Today we're gonna leave it at that, mystery form. And we're gonna focus more on, okay, something happens in my computer, like I don't understand what, that. And once we understand what we're trying to get out of the LDA's models and how that stuff looks like, next week and the week after, maybe we dig into Gibbs sampling. Not as part of LDA, but in general, sampling. How can you guys think about sampling from data when the distributions are complicated? I think it's clear that from an easy distribution, I sample directly, right? Like you did in high school, with replacement, without replacement, right? I can throw a die so many times and I can estimate directly what the expectation of the die is. But when the distribution is very complicated, particular multinomial distributions, it's hard to sample directly. So we're gonna deal with these techniques a little later. I don't wanna make this very mathematical before we even know we're trying to go here with this. So that's LDA, and there's other formulations of it. Like I said, this is one equation, but there's other equations that pretty much mean the same thing. You should not be paying attention to this. You should be having clear in your head this stuff here. What is it that I'm trying to get with those topics? I want the topics to be a function of the words. In this model, it's a probability function. It's a density. And I want the documents to be a density over those topics. Okay? How else can I think of this? So LDA is one. There are two main techniques to do this. LDA, big one. There's quite a few implementations. There's implementation based on EM. People, when they didn't know what to do, they try EM first. But after that, it was shown that Gibbs sampling and other sampling techniques work much better for this problem. But the other major way to think about this, again, maybe you have seen that if you've done some recommendation systems. It's called NMF. Stands for what? Non-negative. M is matrix. F is factorization. This is a technique that is applied to many things. I think the first place in data science what has been applied was collaborative filtering. And it's, if you want, it's based on linear algebra. It's not so different than PCA or that SVD decomposition of matrices, but it has a slight flavor. So if you're familiar with so far with how SVD decomposition works or how orthonormal decomposition works of the covariance matrix, it's a good place to start. So in that, what we want to do is to think of this more like a matrix type of thing. So I'm going to have here a matrix. This is my raw data. Let's say this is A. And as a matrix, I want this to be product of two matrices, W times H. So what's the size of my data? N times D, right? Usually. For this to work, what do I need here? This would be N rows, the same number of rows as my data. N would be times K. I'm using the same K, like in there. And then H would be what? Has to be K times D. Actually, PCA kind of did that, right? You have to think about it backwards. In PCA, we got X nu as this times X. Now, if I want to represent it this way, X is this. This is my raw data. What would X be if I want to say X equal what? P minus 1 times X nu. So I could think of which one would be P minus 1 and which one would be X nu. if I say, okay, I'm going to do this with PCA? Well, the X new has what dimension? Hmm? N times K, that's X new right here. Right? And P minus 1 should be K times D or something like that. So this is a linear algebra. And for people who remember linear algebra from high school, this exact operation, this exact multiplication, theoretically, if you want it to work exact, which never happens in practice, of course, what's the smallest k that I can use for the product to work mathematically exact? There is a theorem that says if you want to do this, k has to be at least the rank of the matrix, right? But that's a theoretical result. In practice, we don't care too much about rank, and we don't care too much about realizing that exactly. It's not gonna, like in PCA, it's gonna lose some information when we do that, right? So there's a bunch of objective of, okay, that's a theory, but what's the objective, really? Like, you cannot hope for an exact product. We can't hope for making A equal exactly the product of these matrices. So we do something like, for example, minimize A minus WH squared. Sum of the sum Aij minus H and J squared. There's other versions of this, which I'm going to show you on a screen. This is more algebraic. There is a version that's based on KL distance that maps these weights for words into probabilities, and then KL distance, it's a distance between distributions. Distribution P versus distribution. So KL distance is a function that takes two distributions and tell you how far apart are they in a particular sense. It's not exactly a distance because it's not symmetric. If you do KL distance of P versus Q, it's not the same as Q versus P. But we don't want to get right now into the mathematical details of KL distance. It's just, I'm saying, if I want to achieve this, and I want to call them topics, I can achieve it in two ways. Either with a probabilistic model, for which I do LDA, and I have to optimize a probabilistic model, or I do it with an algebraic model, for which I'm asking for a decomposition of the row matrix. And then if I have K will be the number of topics, this dimensionality K here. And again, I think if you start off PCA thinking in this way, just take the result of PCA, ignore the fact that using covariance matrix and eigenvectors, ignore all that, say, what is PCA? It comes down to compute this magic P, that's the rotation of PCA, and then P times X. If I reverse that operation, I can imagine this is what happened in reality. So let me connect my computer here and show you a few things. We're going to have to do this in a more technical detail. Not for your homework. So when you run this homework like before, you're going to run a package for either one of those two things. In fact, you're going to do both. And in there, you're going to play with the parameters, and you're going to be required to observe the output, to explain the output. But we're not going to ask you to optimize those functions yourself. You're going to rely on that package, just like now you rely on TensorFlow to do the optimization for you. You're not going to know exactly what the cities are used inside. Okay, so first things first. I think for some reason the website did not update, but I'm gonna try again. This is what you're supposed to see. We're gonna have setup of TensorFlow. I think most of you already have that done. The supervised classification, autoencoders, the word vectors, and the two problems for each. We're not gonna talk about in class, but I think some people already asked me if I wanna do something really interesting with those neural networks, what should I do? Well, I think those two things are what actually being used in practice a lot these days, so it'd be useful to at least know how to manipulate those networks. So that's the homework. And then, I think the homework is gonna be due, next Friday is in 2 days, right? No, I think we changed that. It's, I think, a week from today. Isn't that right? Homework 4, Wednesday 3/21. Is it 14 today? Yeah. So a week from today. I think that's a reasonable time to do the first 4 problems once you have TensorFlow set up, because again, I am assuming most people will find online the scripts that set up things. It's not my intention, but it's unavoidable that you're gonna find online the scripts. However, the TAs will ask you to explain the script, the big picture of the script, not the details. For example, you may be asked a question, where do you define the hidden layer? How many can you change the hidden layer from 20 nodes to 50 nodes? You have to know how to do that. You know, you have to go into your Python code and say, okay, this is how I change it. Can you change that parameters? Can you change that function? Now, you still rely on a lot of Python code written by other people, true, but you have to show that you can control that network somehow, right? It's not enough to download the code, run it, and say, magic happened. I have no clue, but it did, okay? So the TAs may ask you questions like this. Now about the stuff I want to show you here, I asked the PhD student that you will meet next week to run LDA for us and see what happens. He of course ran a package in Python. So that is here. He ran it on a data set first that you don't have. It's related to the information retrieval class, so-called the trick data set. And as a basic output, here's what you can expect. So he asked for 10 topics, right? And he's got things like topic 0, 1, 2, 3. This has a downside that it doesn't print the probabilities. It just prints the top words sorted by probability. So top 9, earthquake, hill, death, police, report, here, those are in the order of probabilities. This is LDA. This is not non-negative matrix factorization. So in LDA, everything is probabilistic. So does it seem reasonable that for some data set, which you don't know, these are relatively distinct topics? What is this topic 9 about? Some sort of natural disaster, as in earthquakes and volcanoes maybe. How about the first topic, topic 0? It has a lot to do with weather and rains and storms and hurricanes like that. In a general sense, maybe if I shrink this from k equal 10 to k equal 3, those might get combined because they're all natural events. But of course, in terms of news articles, I'm guessing those are news articles. They're very different news articles written about storms than about earthquakes.
Everything related to weather.
What?
Almost everything related to weather.
Yeah, but not everything is related to hurricanes, right? I'm not sure exactly what data set he used. Let me see. So how about this topic 2 number is the third one. Fair, cloudy, foggy today, city, sun, rain, windy, snow, Phoenix, Portland, Boston. I'm just, then what we have, Philadelphia, Los Angeles, Miami, Minneapolis. What does this look like? That seems like a typical weather report, right, for most days, like a blunt, okay, in your city, this is what happened. In some city, it's a little foggy, in others, it's a little rainy. It's not, doesn't look like a disaster sort of thing, right? Okay, so what should we get out of topic modeling? This is which part? This is the topics versus the words. How the topics are defined as words. And we would like to see the probabilities, right? But we don't, sorry. No, when he'll come here on Monday, he'll have everything ready. How about this? What is this? These are the documents. These are some IDs from that data set. And those are, each document is represented as a probability over the topics. Those are the topics IDs. And the order, again, we don't have the probabilities, but the order is by those probabilities. Okay, so what I asked Ketchen to do just an hour ago was to do the same for 20 news groups and to do it twice. And I'm not sure whether he did it or not. I just got the results, so let's see together if he did it or not. But I asked him to print probabilities too. So again, I'm looking for the first time at those results, don't blame me. Okay, well, that sounds like we have probabilities. Probably we don't need that many decimals in those numbers, but that's how many we have. So let's see, now we're familiar with the data set. It's the 20 news groups, the same set that you have seen. I'm assuming he took all the documents. Topic 0, 1, 2, he asked for k equal 5 in here. So are those topics reasonably different? So in each topic, he printed the top words by probabilities, right? And I'm assuming those are the probabilities of these words in that topic. So, of course, there could be more probabilities if you keep going, but once you get to very low numbers, maybe it doesn't make sense to keep going further, right? So this is the topics that he's got. Zero, 1, 2, 3. I guess we only have 3. And this is the documents that he's got. So this is the distribution. I'm assuming these are documents IDs, and those are the distribution over these topics of the documents. Now, this is not a very good visualization tool. This is good for debugging if you want to check those probabilities, but there is a Python module that you can do visualization with, and you get something like this. It's, I think, specifically designed for LDA. So let's see if we can. On the left side, we have the topics. And on the right side, we have words. The blues are like general frequencies of the word. So the longer the bar is, the more frequent that word is, I'm assuming. And in here, if I select a topic, I get to see the relevance of the word for that topic. That relevance is computed with the research metric. So for people who know about smoothing, the relevance is computed with the smoothed method between the front probability, that's the word given the topic, and the background probability, of the word. So that's again for people who think found smoothing. Now, this is controlled by a linear mixture here. How much you want to put foreground versus background. And if lambda is 1, you see the lambdas up there. If lambda is 1, it's only this part. It's only the foreground measured in red. If lambda is 0, it's only the background. I'm assuming background means that those red bars start matching the blue bars because the blue bars are roughly the background. Does it make sense? How many people heard of smoothing? I have a background distribution of things that is, say, the word frequencies or something that's in general. Background distribution of the grades. I'm looking for the past 100 years, what is the distribution of grades in the university. But then, if I look at the foreground, I'm looking at the distribution of grades in this class. How many A's, B's, C, D's. So what people do when they want to say, okay, I want to estimate the distribution, they take the foreground evidence, which is for the data they have, but they combine it with the background evidence, just in case they don't have enough evidence. See, if I compute the distribution of grades for only 40 students, it's not enough students to estimate the proper grades distribution. Same thing with words. If I compute the words distribution only from few documents, I don't get the reliable estimate. So smoothing is combining the front evidence distribution with the background distribution. In this case, a very linear smoothing is how much of this you want and how much of that do you want. And by playing with this lambda, we move the red bars into pure foreground for lambda equal 1 versus pure background for lambda equal 0. And anywhere in between is a combination of the two. So again, I'm expecting here that if I change this lambda, I'm going to match red bars with blue bars because the blue bars are the background distribution. So if lambda equals 0, the topic doesn't matter. It's just going to match the background probabilities, right? If I put it in the middle, I'm now the red distribution is a mixture between the topic distribution, which is the foreground, and the background, which is the blue bar distributions. Anyway, apart from that, this is a visualization that says for a particular topic, how the words depend on that topic. So in here we don't see the documents. There's no notion of documents here. This is just explaining how each topic depends on the words. Is the right side of things, right? Because each topic is probabilistic in documents. Now I ask Ketchen to run this again with 30 topics. So instead of 5, we have 30. So on 30 topics, here's what we've got. This printout is different. The properties are indicated right after the word, right? So are those topics fundamentally different now? If I have 30 topics, I should have more granularity, right? I'm not asking to represent the entire 20 news groups into 5 main aspects or classes. I'm asking to represent 20 news groups into 30 aspects. So what is this? Space, NASA, Earth, launch, shuttle, moon, orbit, axis, mission, solar. What is it? Does it make sense as a topic in a semantical sense? See, that's the problem with PCA and some other methods. The dimensions, while algebraically they're correct, they don't make much sense. We want those topics, that's why people prefer LDA, which is far more complicated than linear algebra methods, because they expect the topics to make semantic sense. This whole topic here has to do with cosmos and rockets and planets and all that, like astronomy. How about, I don't know, this one here? Education, maybe? Let's go down, let's try some more. For some reason I can't scroll my. Okay. How about this one? What is it? Operating systems, computers, something to do with IT, right? You see how this stuff makes sense? Now here's a good question for your exam. Run PCA, try to explain the topics, the K things that you observe in there. Now, each one of those is a linear combination of the previous ones. And it might be that those linear combinations are interesting. I don't know. But usually it's much harder with PCA than this kind of method to get a semantic hook into what's going on. Let's look, before Yu goes back to TensorFlow, let's look at this file that is the visualization of topics for 30 topics. So it's the same visualizer. I have a lot of topics here. I think the size has to do with how many documents have mass in there, right? I can, like with the clusters, with the Gaussians, I can say it's a big cluster because a lot of documents have a lot of membership probabilities in the cluster. I think that's what's happening here. This is a bigger topic, and it tells you, here's the distribution of the words of that topic. This is lambda equal 1, so the red one is purely the topic probability of those words. Now, this other topic, 5, has a different ranking, right? So the top words in this 5 are not the same as the rank, of course, in the topic 1.
Is this related to the word of the topic or the document?
This is topics into words. So we don't have documents
So
in
the
here.
larger will mean more words in that.
No. This, I think, I'll have to check, but this, I think, corresponds to the weight on the documents. A topic is big if a lot of documents were on that topic. If you calculate the membership probabilities, you sum up the memberships, now you get bigger topics where you have more documents on that topic, which can happen, right? 20 newsgroups on these topics we just got is not necessarily that's uniform distribution over topics. Right? Maybe there's more documents about this topic. So, as an introduction to this module that we're going to spend about 2 weeks on it, we want to obtain these topics. Very important, we want some semantical sense. We don't want to go in the dark like with PCA, what are those dimensions. We want to focus on visualizations like this. So you're going to be required to run some tool to get visualizations to understand, okay, what is the difference between topics? Why did you get that? What happens if from 30 I go to 5 or to 10? Do I still keep this big topic? The distribution changes or not? But then, you have to be familiar with how to run 2 different algorithms to get topic modeling out. One is based on linear algebra. We didn't talk about that one yet. And one is this LDA, popular package. So now I'm going to let you demo a little bit of the word vectors for TensorFlow. You need a dongle? Do you use the HDMI directly?
Right, so I guess last time we talked about autoencoder for images, right? And then this time we're looking at word embedding, which essentially you can think about it as another kind of autoencoding. But instead of in image, where essentially your input and output are the same, both are the same image, here we're really looking at the context, where your input is your current word, and then your output is your context. So, for example, right, so imagine this sentence, the quick brown fox jumped over the lady dog. So you're essentially, the quick is surrounded by the context, the and brown. So the reason you wanted to encode the word embedding like this, or encode the word like this, is because you wanted to encode all the context information into your representation. So, for example, if you input quick, your output should be the brown. You can imagine that you have a sentence saying the slow brown fox. So essentially the brown, the slow and quick would have very similar semantic meanings in the reduced dimensions, like 300 dimensions, let's say. So this is the whole idea of this autoencoder under the context of text. Of course, like this context largely depends on your data set. For example, if you have a general data set like Wikipedia, you will get more general embeddings. And let's say if you have another data set that it just includes medical data, then your embedding, the meaning, would be more under the context of medical articles. So here's some examples as, I'll go through the code later, but I'll show you the result first. So let's say once you have encoded your a word into a 300 dimension representation, you can essentially print out what is the most closest words that is close. What are the other words that is close to your current word? For instance, I've trained the word embedding on 3 kind of data sets. One is Wikipedia and medical, and then 20 newsgroup. So if you are on the medical data, if you look at condition or conditions, you see closest or semantically closest to conditions are like depressions, I don't know, some disease, I guess. But then if you are going to the Wikipedia sense, then the semantic meaning for word that is closest to conditions are like something like dreaming, sufficiently. You get the sense, like once you change the data set, what it means by semantically closeness is different. Another example is, for example, woman. So here, again, like in a medical context, women seems to be very close related to patients, children, and subjects. And then under the wiki sense, there's, I don't know, supercomputers.
Supercomputers.
So training obviously played
So
a...
men are not related to supercomputers.
woman is. So yeah, apparently there's like, you know, a lot of nasty details about the training process themselves, but the idea is that it really depends on context. Right, so
So by the way, this is why in practice, whoever's serious about this will train or retrain the word vectors for their data. Even though Google has trained on a very large data set and they obtain a good representation in general, for any practical purpose, it's much better to train it for that data set. You see how much of difference is in the similarities.
yeah. So essentially a good practice is that you train within a large corpus of data first, and then you transfer these pre-trained models into your specific data set, so then you warm start your models to use a pre-trained model, and then it will get you better results.
You mean as initialization?
Yeah.
You use the pre-train as
Exactly.
initialization?
Yeah, so here I'm just directly training. I didn't use any pre-trained thing, so it's very obvious that under the medical sense, everything seems to be very related to medical terms. Okay, so I'm going to show another visualization. So this one is just directly looking at the word. There's another way that helps you visualize what's going on. So here is basically the 300 dimension vectors projected into 2D space using TSNE. There's of course you can use other projection method, but you could see that see here, like all the numbers seem to be grouped together in space. So this sort of identify or like shows their semantic relatedness in the original space. Although there's some loss in the projection, but roughly it shows how they are close to each other. So here 2, 3 are together. So again, this is medical.
So hold on. Do you guys remember the visualizer I showed you? That was doing, it's essentially the same kind of picture, or more fancy, but was not projection using TSNE. We never mentioned the word TSNE before. Was projection using PCA. But if you paid attention, there was a projection option, and PCA was by default selected, but TSNE was also a projection method. Now, independent of the projection, why projection makes sense? If I represented my words in 300 dimensions, and I visualize them in 2, I think I showed you in 3. Why does it make sense? What's the purpose of PCA? We said that from the very beginning. PCA tries to maintain distances, right? Tries to maintain distances. So if my projection works, sometimes it doesn't. Sometimes the visualizer will give me a warning, PCA failed because I have a lot of eigenvalues, more than 3 that are still high, right? But if it works, then the distance should be related to the original distance. So it won't matter where those points are, 2D or 3D. What matters is the distance. If I see some word close to another word, it means in 300 dimensions was also close. Again, assuming projection didn't lose too much information. And that's why it's useful for the PCA or TSNE to warn you. I done TSNE like you asked me, but this projection is very rough approximation of the original data. So TSNE, I think it tries to maintain order.
Disney is basically maintain the relative the positions in high dimension space versus in low dimension space.
Position as in order, no? Or positions as in...
Yeah, I guess you can say it's order.
Right. So it's a different objective than PCA. PCA tries to maintain the Euclidean distances. Disney is a projection based on a different objective. Very, very popular, so it's something to look into. It won't matter, I think you can use PCA in here to get the same effect. What really matters for these visualizations is how good the projection is. If projection loses a lot of information, you start seeing things close or far away that in reality are not close or far away. Sorry.
Yeah. So this is essentially the Wikipedia data set. Again, just to give you an example how these embeddings or word are related in high dimensional space projected onto the 2D plot. This is just a tool to help you visualize. So now let's get to how the code works. So this code is actually pretty straightforward that you can easily download online. But really it's, yeah, I'm gonna get it running. So it really takes only a few minutes to run the whole thing. But really this piece of code is, what it is doing is, you essentially just, you have to pre-process the text data first to make it into vocabularies. So really, a lot of times are being spent into getting the right data and then concatenate them into words. And then once you build the vocabulary set, then the step 2, so then the next step is to generate batch, which again is the input data part. So these are all really just preparing for the input data for the graph. So once you have the data prepared, pre-processed, then you essentially starting to going into the TensorFlow, building the graph, and then defining the graph, and then running the session. So essentially the same as the last time. So you define the skip gram model, where I just showed you on the web page. So here's the most important thing is in embedding size. Essentially, this is the key parameter defining how many bits you wanted to represent each word. You can change it flexibly, should be. And then here, you're essentially defining this graph here. So really just there's an input layer, there's an embedding layer, then there's output layer. So this is basically the architecture of the graph. Once you define the graph, then you define the loss function. Here it uses a very specific one. If you're interested, you should read the blog here. Yeah, it has a very detailed explanation about negative sampling. But it doesn't matter to TensorFlow. It's just an API call for that. So you define the loss, and then you define your optimizer, and then you essentially just run the session, like last time I showed you. And then that's it. Once you're done training, then you can take the output, and then you can call package anything that you wanted to project it into 2D, and then just show it out. That's the whole thing. Let's see. So this is running the Wikipedia dataset, which is about 100 megabytes.
So if you wanna impress me, what you can do is to not copy the code from the internet. Is to take the main blocks, main ideas. You can post this on Piazza. Here's the code has to have the following sections. Define the graph, define the batches, define the objectives, da 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 da. And try to, based on your experience with TensorFlow from the other problems, try to build TensorFlow in what you think is gonna work first yourself. If you don't succeed, then look at the code on the internet. I know this will take a lot more time, because if you have to do it yourself in Python, it will take many weeks perhaps. But I think it'd be much more useful for you to understand how this build-up goes without, if somebody shows it to you, it's quite easy to follow. Much harder to try to do it yourself. So while we won't grade this, we won't grade whether you directly got it and just figure out what's going on versus trying to do it yourself. I think it's a much more profound experience with TensorFlow if you try it first and see what you've got wrong when you see the code, okay?
Yeah, so as you can see, it just takes about 3 minutes. But again, I'm running at roughly 100K steps. You can increase it and see how it works out for the visualizer, like, and then you can just eyeball it to see if it gets better or not. Yeah, it's fine.
So remember, we're asking for 3 things in this problem, word vectors. 1, you're gonna get questions about the code. Where is that defined? Where is that defined? Not specific details, but grand questions like how do I change the hidden layer or the word embedding? So you have to have some familiarity with what's going on in there. Number 2, you're gonna ask for, can you put up that list of words?
The list of words, yeah. Right. Let's see.
So what you showed, if I see a common word between 2 data sets, because you may have 2 data sets or 3 data sets to run it on, do I observe different neighbors, different related words, and why is that? For the words that you and other TA is going to ask you for, it should be quite obvious why is women in a medical sense related to those words. Perhaps the supercomputer ones is not very obvious, but in general you should see very different neighbors, which mean very different distances. Right? And you're going to have to do a visualization that asks for a projection. And I think this is a Python
Yeah, so
code that does this.
yeah, this whole thing is essentially just a Python package.
The one I showed you, it's a website that you can load the data in and it loads it for you. Now, if you want to continue this in a more interesting way, as I said, people usually need representation or embeddings not for words, but for tweets, paragraphs, captions, documents, entire books, web pages. So there is an NLP step that says, okay, once I obtain the representation for words, how do I get representation for my documents? So that's an entire track that you can make a project out of it. Because in practice, again, we're gonna need new representations or semantic representation for the documents or sentences or what we have, not for words. You're done, right?
Yeah.
I think we're done for today. Finally, we finish one day before this other. And there will be more demos next week, but mostly TensorFlow will be at office hours. And the demos will be about LDA.